The Ratio Convergence Test. You may not be very convinced with the reasoning used in the last 3 or 4 series about their convergence or divergence. Therefore, we use another rule about the convergence or divergence of a given series called the ratio test of convergence. This test consists of calculating the limit of the ratio between 2 consecutive terms when the number of terms points to infinity. Here we will discuss the concept of limit very superficially, as much as we need to explain how to make the ratio convergence test, as we will explain more extensively the concept of limit in the corresponding chapter. All what we can say here about this concept is that the limit of a function is the result obtained when the variable points towards a given number. For example, the limit of 3x plus 5 when x points towards 12, we have the following shown on screen. Therefore, we say, when x points towards 12, then 3x plus 5 points towards 41. If we want to find the limit of a rational expression when the variable x point to infinity, we consider only the highest order terms of the corresponding polynomials. In this case, we simplify the monomials obtained, and if any variable is left after this simplification, we substitute its value by the infinity. This is because the value of a polynomial increases at a higher rate in the monomial with the highest degree, so the rest of terms are irrelevant. We have the following shown on screen. And so on. But now, let's get back to the point, i.e. to the ratio test of convergence. Let sigma, a, n be a series with positive terms, where a may be a variable, a monomial or an entire algebraic expression, and let's suppose that we have the following shown on screen. The ratio test of convergence rule says that, if L less than 1, then sigma, a, n is a convergent series. If L greater than 1, then sigma, a, n is a divergent series, and if L equals 1, then the convergence test of sigma, a, n is inconclusive, i.e. we need to use other methods to study its convergence. In fact, we have silently used this ration test in previous cases in this tutorial. For example, in the P series with P equals 2, we have found a, 1 is equal to 1, a, 2 is equal to 1 over 4, a, 3 is equal to 1 over 9 and so on. Therefore, when we divide n plus 1 by n, the result is always a number smaller than 1. Example. Use the ratio test of convergence to check the convergence of the following series. A. Euler series, we have the following shown on screen. B. Harmonic series, we have the following shown on screen. C. We have the following shown on screen. Solution. A. We have for the Euler series A, n equals 1 over n. And A, n plus 1 is equal to 1 over n plus 1. Hence, we have the following shown on screen. Hence, since the limit L equals 0, the Euler series is convergent, from the first condition of the ratio comparison test B. We have for the harmonic series A, n equals 1 over n and A, n plus 1 is equal to 1 over n plus 1 hence, we have the following shown on screen. Since L equals 1, the convergence of this series cannot be defined through the ratio convergence test. C. We have for the series S, A, n equals 2, n and A, n plus 1 is equal to 2, thus, we have the following shown on screen. Thus, since the limit L is greater than 1, this series is diverging. That is all for lesson 12.4.6. To continue this tutorial, please watch 12.4.7, the root convergence test. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.com.